The modern understanding of space, time, and the universe can be dated back to 1916, the creation of the theory of general relativity by Albert Einstein. In 1922, the Russian scientist Alexander Friedmann developed Einstein's theory further and suggested a hypothesis stating that our universe is expanding. This hypothesis was followed by an important conclusion that at the very beginning, all matter of the universe was concentrated in a small volume from which the expansion began. This expansion could be caused by an explosion. The next step, comparable to the contribution of Copernicus, was made by the American astronomer Edwin Hubble, who in the 1920s worked using the largest telescope of the time. Not only did he discover many other galaxies beyond our galaxy called the Milky Way, but he also found out that the greater the distance between the galaxies was, the faster they moved away from each other. Thus, he experimentally proved that the universe was expanding. In 1948, the Russian theoretical physicist George Gamow assumed that if the universe had originated as a result of an explosion of hot dense matter, then somewhere in space there must have remained traces of that event. In 1964, the American radio astronomers Arno Penzias and Robert Wilson discovered radiation currently known as the Relic background. The temperature of this radiation is now 3 degrees K as predicted by Gamow. Modern science believes that the universe was formed 13.7 billion years ago as a result of an event that is now called the Big Bang. That is, scientists figured out that the universe had a beginning. Now they have to answer another important question. How exactly was the universe born? What bricks of matter does it consist of? What do we know so far about the world around us and the structure of matter? Everything that surrounds us on the planet Earth, we ourselves and all living things, is made of tiny particles, atoms. The word atom in Greek means indivisible. However, modern science knows that atoms consist of an atomic nucleus and electrons. The size of the atom is very small, about 10 to the negative 10th power meters, and the size of the atomic nucleus is 10,000 times smaller than that. The atomic nucleus consists of protons and neutrons. Protons and neutrons, in turn, are also divisible. They consist of quarks and gluons. Despite the fact that quarks and gluons are called the bricks of matter, no one has ever observed them in a free state. As the distance between quarks increases, the restraining forces become so great that quarks cannot leave the proton or neutron. But it has not always been the case. In the early universe, there existed such high temperatures and matter densities that quarks and gluons manifested a special state of matter called quark-gluon plasma. What happened in the first moments of the birth of the universe? How were protons, neutrons, and atoms formed out of quarks and gluons? Modern physics is looking for the answers to these questions.
So what do we know about the history of our universe? About the history of the world around us? At the moment, according to modern scientists, we know that the universe was formed 13.7 billion years ago. It happened as a result of the Big Bang. The Big Bang was a phenomenon that occurred at unimaginably small distances, 10 to the negative 33rd centimeters, within very short periods of time, 10 to the negative 44th seconds, and the density of matter that was formed as a result of the Big Bang that is, the density of the earliest universe, was equivalent to 10 to the 94th grams per centimeter cubed. In a very short period of time, approximately 10 to the negative 34th seconds, the universe, as a result of inflation, that is, a very rapid exponential expansion, the universe expanded to about 10 centimeters. Thus, as the result of the Big Bang, when the inflation was over, several types of elementary particles, elementary bricks of matter, were formed in the universe. Quarks and gluons, electrons and gamma rays or photons, and neutrinos. And at that very moment, in about 1/1,000,000th of a second after the Big Bang, quarks and gluons, interacting with each other at colossal temperatures and densities that surrounded them, formed quark-gluon matter. Later, while the universe was expanding and cooling, protons and neutrons began to form. Quarks, according to some laws we are currently unaware of, were grouped into pairs and triplets, forming protons, neutrons, and mesons. In approximately 3 minutes after the Big Bang, the universe consisted of protons, neutrons, electrons, gamma rays or photons, energy carriers, neutrinos, and other elementary particles and carriers of interaction. And the temperature of the universe was so high that in thermonuclear reactions, light elements such as hydrogen, helium, and lithium could emerge. With further decreasing temperature, the nuclei of the lightest elements captured electrons to their shells and formed the first neutral atoms. And from that moment, about 300,000 years after the Big Bang, the so-called relic photons were formed. These were energy carriers, gamma rays that no longer interacted with protons, neutrons, or electrons. Ever since, these relic photons have been traveling in the universe, and they are now helping us recreate the picture of the universe's evolution after that moment. In fact, photons of the relic radiation have witnessed all the events in the universe that have occurred since 300,000 years after the Big Bang. And observing them, studying these particles with telescopes and other astronomical instruments, we can reliably speak about the history and the evolution of the universe since 300,000 years after the Big Bang. And in order to observe and thoroughly study and be sure of what was happening at the earliest stages of the universe's evolution, we need a time machine. An accelerator can serve as one, because with the help of an accelerator, this absolutely wonderful device invented by humankind, it is possible to create extreme temperatures and densities in the lab.